Alright, so in this video we're going to go over integrals involving trig and squared trig, which is where it gets very interesting. And we'll also look at some inverse identities as well a little bit later in the video. But before we get started, unfortunately you do need to remember some stuff from pre-calculus for some of these problems, because often it's easier for us to find it in one form rather than another. So especially when we get to squared trig, these forms are much easier for us to antiderive than the actual squared forms. So that's something you want to keep in mind. So these are the double angle options for cosine, and then this comes from the Pythagorean identity. If you take the sine squared plus cosine squared equals 1 and divide everything by sine squared. You can also divide everything by cosine squared if you happen to have something with cotangent and cosecant squared instead. So let's jump in. So some of these we already know. So we've been integrating sine x and cosine x for a while, so hopefully these won't seem quite as scary. So the antiderivative of sine x is simply going to be negative cosine x plus c. Remember that our cos are negative. That's how I try to keep things straight. The antiderivative of cosine is our favorite because it's simply sine x plus c. Then we get the antiderivative of secant squared, which again we like because that's simply tangent x plus c. So then of course for cosecant squared it's just going to be negative and the cotangent x plus c. So these are two squared forms that actually aren't so bad. In fact, it's when it's not squared that it's more tricky for those. Alright, so then we get to one like the antiderivative of tangent, and this is where you have to be careful because this is not the derivative of anything. There's nothing we derive and get tangent or cotangent from. And so we have to be creative. So we're going to rewrite this first as the integral of sine x over cosine x dx. And we're going to use your favorite method, which is U-Substitution. And often you need to just be smart about it. So both of these can be formed into the other as far as how the derivative goes. Usually I like to pick the denominators just because it's harder for me to derive sine and somehow get 1 over cosine. And we don't want our du in the bottom. We want it on the top because that's really when it's just being multiplied. So traditionally you're pretty much going to pick this denominator term as your u. So we're going to let u equal cosine x. So du equals negative sine x dx. How to think about that. Now we're going back and forth. That's where things get interesting. So if we solve, here we have just plain sine x dx. We don't have a negative with it. So we're going to divide both sides by a negative and get negative du equals sine x dx. So when I rewrite this, I'm going to get the integral of that becomes 1 over ru. And then we're going to multiply by negative du. Alright, so I'm going to pull that negative out front. And I'm integrating 1 over u du, which is simply the natural log. So we're going to get natural log of u, and I'm going to go ahead and plug back in what our u is. Our u is cosine x plus c. Okay? And so cotangent is going to be very similar. Of course, it's just going to be flipped. So, oops, for this one we're going to get the integral of cosine x over sine x. And again, that denominator is where we're going to go. So I'm going to let u equal sine x. So du equals cosine x dx, which I have right here. So I don't actually have to do anything crazy here. It's pretty straightforward. So I'm going to get the integral of 1 over u du. And so this one is also going to give me an ln of our u, which is sine x, and then a plus c. So those aren't too bad because we can just break them up into their ratios. The ones that are much less intuitive are cosecant and secant. So again, when they're squared, no big deal, because those are already derivatives of something. But when they're not squared, it's actually a little bit weirder. We have to somehow make it squared, basically. And then we also have to kind of think ahead and ask ourselves, like, what's the derivative of this piece? So what am I blabbing about? Well, we're actually going to introduce a new term here. We're going to multiply by 1, but in a very creative way. We're going to multiply by cosecant x plus cotangent x. Okay, so on the top and the bottom. Now, obviously this is very much a specific choice, and we're choosing it for a reason. And the reason is I'm trying to create things that I like have derivatives of, right? So, or antiderivatives. So I'm trying to create things that are derivatives of something else. So cosecant times cosecant will give me cosecant squared, which is the derivative of negative cotangent. So I know that'll work. And then I also know that if I derive, not integrate, but if I derive cosecant, I get cosecant cotangent. So that's where this is coming from. Okay. Remember, this is like it's over 1, so we're just going to multiply across here. So now we're taking the integral of cosecant squared x plus cosecant x cotangent x over cosecant x plus cotangent x dx. Okay? And so we're going to have to do our U-substitution here. And the main reason we're going to have to do that is because of this denominator. So we're going to have to let our u equal the denominator. So then du, this is how we're getting the numerator. Okay, oops, I forgot a plus sign there. Let me rewrite that. So cosecant x plus cotangent x. So this is where we were going with this. So the derivative of cosecant is cosecant cotangent, cosecant x, cotangent x, and it should be negative, I'm pretty sure, because it's a co. And then the derivative of cotangent is negative cosecant squared. Oops, that's not how we spell that. Okay, dx. Alright, and so I have this cosecant squared x plus cosecant cotangent x dx. So basically I need to factor out these negatives, and then I'll have that in the numerator. So if I move the negative over to the du side, I get what I'm looking for. Cosecant x cotangent x minus cosecant squared x dx. So this means this big nasty integral really is just going to end up being 1 over u du, which looks very familiar. The only thing that's different is we have this little negative in front of the du that we're going to pull out front. So I'm going to get negative, and then the antiderivative of 1 over u is ln, and u is cosecant x cotangent x. Actually, I'm doing a lot of steps in one. I don't want to lose you guys here. This one's already pretty confusing. So then we'll plug in our u. So we'll get cosecant x plus cotangent x plus c. Alright, and secant is going to be very similar. In fact, the only thing that will be different is it won't have a negative because we're not dealing with cos anymore. And instead of cosecant x plus cotangent x, I bet you can guess, it's simply going to be, let's see, the natural log of the thing itself, and then what his partner in crime is. So like cosecant and cotangent go together, and secant and tangent go together. And we can work through this one in class, but it's literally the same exact process. These are not super common, so I don't want you to stress about, oh my gosh, how will I know what to put here, and this seems really confusing. It is confusing. It's also not very common. So we're going through it just so you can see it, but it's not something we typically are going to have to deal with. Alright, for our next problems, we're going to be using those identities I mentioned at the beginning of the video, because we're going to be anti-deriving some more squared functions, so like cosine and sine. We're going to rewrite them in these forms. Now I'm going to be honest, I don't memorize these. I'm really bad at memorizing. I can remember this identity for cosine of 2x, and that's about it. And so how do I get here? I simply could add 1 over and then divide by the 2, and then I've solved for cosine squared. And then, of course, for sine squared, I would just use some sort of Pythagorean identity to plug in here, right? So if I think of this as 1 minus sine squared x being squared, or no, sorry, being multiplied by 2 and subtracting 1, that would give me 2 minus, what, 2 sine squared x minus 1 equals cosine 2x. So if we're solving for sine squared x, right, 2 minus 1 is simply 1. And so we're going to have that as part of it. And you can see this right here. This is where that second form comes from. They just combine these. So if we're solving for sine squared x, you would subtract 1, then divide by a negative 2, so it would switch those signs. So that's where these come from. Really, all you need to know, I don't remember any of that. I just do it as needed and remember this one. Okay? But we're going to use those now for our next examples. Alright, so let's rewrite this first as the integral of 1 minus cosine of 2x over 2 dx. I'm actually going to break this one apart. I'm going to use our algebraic technique of splitting the numerator. So I'm going to get the integral of 1 dx, or sorry, 1/2. 1/2 dx minus the integral of cosine 2x over 2 dx. Okay, and really, actually, let me shortcut that even more. I'm going to take this out front, so I don't even have to deal with that fraction either. So, sorry, it looks a little floaty. I'm just going to have cosine 2x here, dx. And so now the first piece is pretty easy, right? That's just going to give me 1/2 x. That's not too bad. And then the second piece, I am going to have to use U-substitution for just slightly because we have a cosine of 2x. And so du would equal 2 dx. And so we're going to get a 1/2 du equals dx, which is all we have right there. And so I'm going to end up with 1/2 minus 1/2 times cosine of u, and then times 1/2 du. So then that's going to look like 1/2 x, and then I'm going to pull this 1/2 out with the 1/2 already there, which becomes 1/4. Okay, and then we're anti-deriving cosine u du, and so we're going to get 1/2 x minus 1/4. The antiderivative of cosine is a negative sign. No, it's not. It's a regular sign. Whew. Sine x plus c. And that's it. So now cosine squared versus sine squared, they're actually very similar. So if we look back at these, I guess, altered forms, this one has a plus for cosine, the one we just did. Sine just has a minus. So it just has that one sign difference. So what we're going to do is essentially just kind of use that pattern. I'm not going to work through this one right now all the way through. We're going to think of it as the integral of 1 plus cosine 2x over 2 dx, and think about what would be the same and what would be different. So everything, like the 1/2 would be the same, so this part's not changed. Even the cosine 2x over 2 would be the same, right? The only difference is there's a plus instead of a minus. Okay, so we're really going to get the exact same thing, but with a plus. I know that's not the most exciting, but we're going to get 1/2 x plus 1/4 sine x plus c. Oh, Miss Wright. Miss Wright did something very wrong, and I just realized it. This should not be an x, because our u was a 2x. I hope some of you caught that. My bad. That kind of makes a difference. All right, there we go. All right, these last two squared terms are actually much easier because we can use Pythagorean identities with these to kind of get them into squared terms we are familiar with. So tangent squared x, we're looking at this first one here from the Pythagorean identity. We can rewrite it as secant squared x minus 1, which will be much nicer. So we're going to rewrite it as secant squared x minus 1 dx. Sorry, I'm so squished here. And so then that's going to be the antiderivative of secant squared is tangent x. The antiderivative of minus 1 is simply x, and then a plus c. And so that should be it for that one. And then cotangent squared is going to be very similar. Let's derive that real quick. So we would have sine squared x plus cosine squared x equals 1. And then we're simply going to divide by sine squared x to get this third form. Okay, so that's going to become a 1. That's going to become our cotangent squared x. And then that's going to become our cosecant squared. So the one we're working on is cotangent squared. So that's simply going to be cosecant squared minus 1. So obviously, I guess I could have probably seen that because it's very similar to the one we just did. So this is the same as finding the integral of cosecant squared x minus 1 dx. That's going to give us negative cotangent x minus x plus c. Alright, now that we're done with regular trig, we're going to move on to inverse trig, which actually I prefer in these cases, but you can give me your opinion later. So again, remember the denominators are the key, okay? So we're looking for the square root of 1 minus something squared, or the absolute value of something times the square root of that something squared minus 1, or 1 plus something squared is probably the most common one we'll see. And you'll also notice that the numerators do not have expressions in them. They have to have some sort of constant that we, if needed, could factor out front. So here's our steps. Identify the inverse trig formula. Again, that denominator helps us with that. Get the constant in the numerator to be a 1. Factor out whatever you need to. Write the x part as something in parentheses squared so that it's very clear what we're going to use our U-substitution for. So let's take a look at example K, I suppose. So in this case, I would first rewrite this. So I see something that's a perfect square minus x squared. What I really would like to see is a 1 minus x squared. So I'm going to try to find a way to factor this 4 out of the square root. So that's our goal here. So this is going to become... When we factor things out, we have to do it inside the square root first. So that would become 1 minus, and then that would become x squared over 4, since we're dividing it out. I'm also going to pull the dx out to the side, because that's what I prefer, so that I see a 1. Okay, so then this is going to become that 4 we're finally going to pull out of the square root, so it's going to become a 2. And then I'm left with 1 minus, and then I want to think of that x squared over 4 as something being squared altogether. So the x would be on top, and then what squared gives me 4? 2. So I want to write it in this form because we're going to do U-substitution with it, and it just makes it pretty easy to see where we're going with that. So I'm going to let u equal x over 2, or 1/2 x. That might be easier to see. So then du is simply 1/2 dx. However, I do not... Well, actually, do I have that? Let's see. I do, because I have 1/2 and I have dx. So we're actually good here. We're just going to end up with the integral of 1 over the square root of 1 minus u squared du And so then we're able to see how it represents inverse sine of that u. Plus c. And so we get inverse sine of x over 2 plus c. And that's it. Alright, so then when I look at L, I don't see square roots, but I see a perfect square plus something that's a perfect square. If it was minus, we could try to factor and do difference of squares, but the plus is the key. So I'm going to rewrite this one. I'm going to pull the 3 out front from the numerator so that I get 1 over. Let's see. I need a 1 plus x squared somehow, so I'm going to factor the 16 out, kind of like how we did with the 4. So that would be 16 times 1 plus x squared over 16 dx. Alright, so now we're going to get it ready for U-substitution. So what I'm going to do for that is I'm going to write this term here as something squared. And I am going to go ahead and factor out that 16 in the denominator because when we rewrite this, we're going to get an x over 4 squared. So the 16 isn't as nice as the 1/2 was last time. Alright, so u equals, I'm going to write it as 1/4 x. So du equals 1/4 dx. But I do not have that. I'm kind of just leaving these outside of that train of thought. So to me, all I have is a dx. So I'm going to have to multiply by 4 on both sides to make that substitution. So I'm going to get 3 over 16 times the integral of 1 over 1 plus u squared times 4 du. Okay, so when I factor this 4 out front, it's going to simplify with the 16 and leave me with simply 3/4. And then I'm integrating 1 over 1 plus u squared du, which is simply inverse tan or arctan. So that means I'm going to get 3/4 inverse tangent of u plus c, and then we're just going to plug in what our u is equal to, which is 1/4 x, or x over 4. Awesome. Alright, and we're going to do these last couple examples in class. We're going to cut it there. So this concludes our video on doing integration with trig and inverse trig with U-substitution.